And hello YouTube, welcome to this video of boundary layer equations. So I assume you know about Navier Stokes equation and some of the terminology that is used. Because if you see if you search Wikipedia for Navier Stokes equations, you will arrive on the page, and then you might see some things that make it a little hard to read. Okay, what I mean is that you will see symbols. Okay, you will see symbols that are a little challenging at first. Okay, so you see things like this this tensor product O times, or whatever it is. O times is what we use in LaTeX. Okay, and you will see a dot product, or a dot product of a tensor. So when you have the outer product of two vectors, you get a tensor, and you take a dot product of a tensor. It's not really a dot product anymore, it's called an inner product. So I assume you know what all these are. If not, don't worry, you can actually look at one of my YouTube videos. They show in this same fluid mechanics playlist. It will be listed in the description. Okay, yeah, in my fluid mechanics playlist you will see some things relating to fluid mechanics, of course. So Navier Stokes and everything, all of this will be in the description. And of course, I have my GitHub over here. Fluid mechanics will be under heat transfer theory YouTube, this GitHub repository, and this is what I'm going to paste inside the description, so you don't have to worry. Okay, this will be in the description itself. Why is it under heat transfer and not fluid mechanics? Because you need to understand this fluid mechanics in order to understand convection heat transfer. So fluid mechanics will be under convection heat transfer, and I'm approaching fluid mechanics from a heat transfer point of view. Okay, but for these few videos on boundary layers, it doesn't really matter whether it's what do you call that, yeah, whether you're coming from aerospace or chemical kind of point of view, whatever. Okay, doesn't matter here. So these are kind of common throughout all branches of engineering. Okay, so let me get to the PDF, the LaTeX PDF. So I kind of covered some of these preliminaries in the last video, what all these tensor products and this inner product is about. This inner product actually reduces to a dot product if you do it between two vectors. Okay, so we start from the incompressible Navier Stokes equations. Okay, and let me put the GitHub here. Okay, so this is we start with the incompressible Navier Stokes equations. We want to reduce this to the boundary layer equations. Okay, so that will be the 2D Navier Stokes equations. So we go from 3D to 2D. So first order of business is that we want to expand this this term over here out into the so-called vector form. Okay, this is vector form. I just want to see every single element inside these two this vector over here, and of course you have this Laplacian term here, which is actually the viscosity term. The other way you can view it is that momentum is diffusing from one area to another. Okay, why do we say that? So these are the boundary layer kind of things I kind of covered the last time in the preliminaries video. Now we actually start proper, a little more proper. There's still you still cover the Navier Stokes equation first. But why is it called momentum diffusivity? Alright, so picture yourself having two blocks of stale fluid. That means the fluid is not moving at all. Alright, and then you have in the center of this, you have a block of fluid maybe moving at 5 meters per second to the right. Okay, so if you have some sort of viscosity, if all of this is the same fluid, and you have some sort of viscosity mu, or you have the kinematic viscosity, which is nu equals to mu over rho. Okay, in this case, it just has the fluid just has a viscosity. Both dynamic and kinematic viscosity kind of explain this, help to explain. But so let's say you have a viscosity here, and you take a look at this part here. So if you zoom in here, all right, you can take a look at this block of fluid. At the bottom, it's moving at 5 meters per second. All right. So having a having fluid viscosity, it means that the fluid actually exerts friction on neighboring portions of fluid. Okay, so this fluid element here, this fluid element. Okay, there's a fluid element here. It's going to exert a force on this fluid element, of course, to the right. And by Newton's third law, this top fluid element actually exerts a force on this fluid element over here, thus pulling it to the left. So this is the frictional force, so to speak, and this is the frictional force here. So this bottom fluid is dragging this top bit of fluid to this fluid element to the left, to the right. I just call this Fe. I'm a bit lazy, yeah. Okay, this bottom fluid element is dragging this top fluid element to the right, and this top fluid element is, by Newton's third law, dragging this bottom fluid element a little bit to the left. So what happens? Maybe at the next time step, maybe you'll have the velocity at 4.8 meters per second, and then the velocity here will not be 0 anymore. It will be 0.2 meters per second. Okay, so what actually happens? So the momentum is like mass times velocity, right? This mass times velocity, mu. Now you'll notice that initially where you had a block over here moving at 5 meters per second to the right, now this momentum has actually, the momentum of the center block has dropped a little bit because of these frictional forces, and the momentum of the top block here has increased a little bit. So the overall effect of viscosity is that this momentum of the center block actually lowers, and the momentum of the adjacent blocks actually increases. And in other words, momentum is actually shifting from this center block to this adjacent block. So the other way of saying this is that momentum is diffusing outwards because of viscosity. So that's why we call it momentum diffusivity, which is this kinematic viscosity is also called momentum diffusivity. So that's just for your knowledge in case we bump across this term again. So let's expand this term out. Okay, so we have a divergence of u. So I'm going to start an equation. So divergence will be, I'm going to start a matrix here. P matrix fraction partial by partial x, and then I'm going to double backspace, and I'm going to of course copy and paste because lazy, and we want to do things quick, right? Partial by partial x, partial y partial y, and partial y partial z. Alright, so this is what the gradient operator looks like. So we want this gradient operator. Okay, it's a bit squeezy of course, but we want this gradient operator to operate on the vector u. So when we do the gradient operator on the vector u, we use the tensor product again, and let's put this down. Okay, I'm going to do a P matrix. Okay, u1 double backspace, u2 double backspace, u3, and I'm going to show you. Okay, we're going to do this very slowly. How do we do this tensor product? Okay, so we need to take the transpose of this gradient term. Okay, so let's take the transpose of this gradient term. P matrix. So partial by partial x, y, and z. So instead of this double backspace, I'm going to use double N, because that's going to denote the use of the changing columns. Alright, and next I'm going to multiply this by, I'm going to multiply it by this vector over here. So I'm not going to use times or anything, but I'm just going to write it here as such so that you can see we are just doing a multiplication. Vector multiplication. Oops. I think I wrote something wrong there. Alright. We are supposed to take the transpose of the outside. Okay? This is the outer product. So we take the transpose of the outer vector. Oops, I got it wrong. Okay, let's try again. This is P matrix here. And oh shucks. Okay, let's do it. We're going to shift this down, copy and paste it here, and then I'm going to multiply it by this matrix here. I'm not going to use a lot of P matrix using the end. So I'm going to change the double backspace into end. I'm changing the LaTeX code here, so that should give the right expression if everything goes right. Yaha. Right, let's try again. Yeah, looks good. Yes, okay. So the vector multiplication goes like this: first row, first column, first row, second column, first row, and third column. All right. So I'm going to insert some $ parentheses here. Okay, so I'm going to begin a whole new P matrix. Okay, so just do partial by partial x of u1, and then partial by partial x of u2, partial by partial x of p3, u3. All right, u2 and partial by partial x of u3. Okay. Then next one is going to be the partial by partial y, which is over here. So I'm going to compile while waiting. Alright, so partial by partial y of u2, u1, partial by partial y of u2, partial by partial y of p3. So we'll just repeat the whole thing. And just for the speed of it, I'm just going to type in this new column here. Just copy and paste, change the x to y, and the last one we are going to do the same for partial by partial z, is the z part. Okay, so 1, 2, and 3. So this is how tensor products are being done. All right. So now we have this. We'll need to do the what do you call that? The inner product on it. So let's do the inner product. So yeah, inner product will be this. All right. Begin P matrix, then bullets. I'll put in this whole matrix here. Okay. I'll put in the whole matrix in there, and we'll need to transpose the first matrix. Okay, so what term am I dealing with? I'm dealing with this term over here. Okay, I'm dealing with this term over here. Okay, first let's deal with All right, I'm dealing with this term over here. So that's why we are doing first the gradient of u. Okay, the gradient of u. Then we take the then we take this what do you call that? We take this dot product, inner product. Sorry. Of course, you can do the inner product as well first, and then you put this take the you just multiply this scalar into all of this u1, u2, and u3. No problem. In fact, that would actually be a lot faster than what I'm doing here. Oops. So maybe that I made a mistake in that regard. But yeah, you can take the dot product of this divergence term and u, and then you just multiply this scalar into the into u over here. Okay, but either way you'll get the same, more or less the same results, if I'm not wrong. Okay, but yeah, how I'm doing it is I take the gradient of u and then I do an inner product with this velocity vector. So that's what I'm doing over here. How do we take the inner product? We transpose this thing first, and then we just multiply it out to find the 3 elements of the vector. Of course, it won't be I think it will be a column. We'll see. I can't remember. I'm not really sure if it's going to be a column or row vector. So let's see. We'll need to transpose this bit first. So let's transpose that bit. All right. So we'll transpose this thing, and then we'll just paste this matrix over here. Alright, so u1, u2, u3, and then we'll just dot multiply it by this matrix. Alright, I don't need to put the dot product there anymore. And yeah, let's see what this is equal. So first thing we need to do, we'll multiply this whole row by this column. You'll multiply this whole row by this column here. That will be the first row, first column kind of a thing. So u1 times del by del x u1, u2 by del y u1, u3 by del z u1. So that's the first sum. Okay, so P matrix. Alright, so okay, u1, and we'll have the del partial by partial x u1 plus, alright, I think there's a faster way. Alright, I'll just do this. Okay. Alright, that's not the okay, I guess I have to type it out manually then. Okay, next is u1, u2 partial by partial y. So u2 partial by partial y u1 plus u3 partial by partial z u1. Okay, so this is just the dot product here. 1, this times this, plus this times this, plus this times this. That will give you the first part. Alright, I think I forgot the parentheses there. Okay, and actually I want to kind of transpose this whole matrix, so I think I'm going to change my definition here a little bit. Actually, this whole matrix, in the inner product, I want to transpose it as well. Alright, so that it will come up as a vector, a column vector. Okay, So let's see. Yeah, see, I rather transpose this. So so this dot product, when if you transpose it like that, it will be okay. Whether it's a what for two, if you take a inner product of two vectors, you just basically get a dot product. And whether it will become a scalar. So whether you transpose it or not doesn't really matter. But when you start doing inner product of a vector and a tensor, then it gets really messy. So 1, 2, and 3. So this sum is the first element. We'll need to do the second element as well. Okay, I don't want to put it in the second row. I want to put it in the first row but second column. Okay, so I'll transpose it. All right. So that will be, the second one will be u1, u2, and u3. The same. The outside terms are the same, but the inside terms, instead of being u1, they become u2, 1, 2, and 3. All right. So, and for the third column is basically the same thing. All right. Instead of the terms inside here being u1, it will be u3 for the third column. All right. So I just copy and pasted this second row to the bottom here. I'll just need to change the velocities on the inside to become u3, or the z velocity in other words. All right, so okay, so this is a vector, okay, column vector with 1, 2, and 3. All right, 3 rows and 1 column. Okay. Okay, suffice to say, I don't really know if I have too much time to do this second part, this Laplacian of U. Okay, but if you were to let's say do the same processes I did here. Okay, the same processes I did here, you will basically get, when you get a Laplacian of U, you will also get a vector here. Okay, you also get a vector here. Okay, I will try to save time a little bit. So when you have this Laplacian over here, this Laplace, which is a del square or nabla square, what you do is just you basically replace the U here by del x, del by del y, and del by del z. You replace this u here by the divergence operator if you want to take this Laplacian. So I'll try to go through this a bit quickly. Okay. Nabla square equals to nabla bullet nabla. Alright, so and of course I will just copy and paste this whole inner product and I'll just replace it. So you see, nabla square is nabla times nabla. So whatever I have this u1, u2, and u3 here, I'll just replace it by del x, del by del y, and del by del z. And basically we will get the same effect. Okay, so how do we deal with this? Okay, so let's just paste the gradient operator here. So to do that, I'll copy and paste the gradient operator. So notice over here, notice over here is u1, u2, and u3. I'm just going to replace all of this by the gradient operator. Okay, I'm first going to copy all of this down, and I'll just replace it. Okay, and this part we are dealing with the momentum, diffusivity, kinematic viscosity term. Alright, so first thing first, I'm just going to replace all of this here. So I'm replacing this part over here with the gradient operator, and now of course I'm going to take the transpose. So I have to transpose this thing, and this whole matrix here, this whole resultant row vector here, I'm going to transpose to a column vector. Okay, so we are doing this 1, 2, and 3. So del by del x u1, del by del y, del by u1, del by del z u1. So you have a Laplacian operator here. So I'll just swap out the u1s here for del by del x, swap out the u2s here by del y, and swap out the u3s here by del z. It is pretty much that simple. Okay, so this is what the Laplacian operator looks like. Okay, so first thing first, swap out the u1s. Okay, swap out the u1s by del x. Swap out the u2s by del y. Okay, so I'm swapping out here. And of course, the last part is to swap out the u3. The u3 is over here by del z. As follows. Okay, 1, 2, 3. Hopefully I pasted in the right areas, but this is basically our Laplacian operator. So del by del x u1, del square x u1, del square y u1, del square z u1. So with these two vectors in mind, we can actually start presenting our so-called Navier Stokes equation in 3D. Okay, and alright, and of course this gradient operator is here. We can start doing this in the next video. Okay, but I'll kind of just stop here for now. Alright, just expand this out first, and yeah, that's it. So it's a little tedious, but you can see why people actually write Navier Stokes equation in this form. It is because it's very shorthand. You don't have to write 9 terms out over here. Okay, there are lots of terms to actually write over here, but you can compress the x momentum, the y momentum, and z momentum terms into one shot vector equation, just like that, because and it's a lot easier to write. It's just that expanding it out into the terms that we are familiar with may not be that simple, or may be a bit tedious, as what I'm showing you here. Alright, so once we are done expanding this, we can actually convert into 2D and start with our boundary layer equations. So I'll just stop for now. I'll see you guys next time. Bye bye.